First thing I'm going to do is determine if this point is a solution to this entire system. And if it is, what that means is it's a solution for this equation and this equation. That's the only way it can be a solution to the entire system. And in fact, this is going to be the one point where these two graphs, the graphs of these two equations, touch, where they intersect one another. So I plugged in 1 for x, and we're going to put 5 times, instead of 5 times x, 5 times 1, minus 2 times y, which is 5, equals negative 5. I multiply before I subtract, so I have 5. Negative 2 times 5 is negative 10. Bring down my negative 5. I'm going to circle my terms because I'm going to combine them, and it's easy to see I have more negatives than positives. In fact, I have 5 negatives left over. And look at that. This is a true statement right here. So 1 comma 5 is a solution of this equation. Now the question is it a solution of the second equation? So let's give it a try. So here is my function table. I'm just going to extend it. I'm going to put my second equation in here. And again, I'm going to plug in 1 for x and 5 for y. So I have 3 times x would be 3 times 1 minus 7 times y. Y is 5. And that equals negative 32. 3 times 1 is 3. Negative 7 times 5 is negative 35. I'm going to circle my terms, and it's easy to see I have a whole lot more negatives than I do positives. In fact, if 3 of these 3 positives grabbed 3 of these negatives and married them, I'd have 32 negatives left over going wah, wah, wah. But I noticed that this is a true statement. So 1, 5 is a solution of this equation. So if this is 1, 5 is a solution of, oh, I'm so sorry. Look what I just did. I'll give you a second to look at that. If 1, 5 is a solution of this equation and 1, 5 is a solution of this equation, then 1 comma 5 is a solution of the entire system. So if I graphed these two equations, the one point where they would intersect or touch would be at 1 comma 5. And I can figure that out without graphing just by plugging that in. How cool is that? Extremely. Okay, let's try number 2. We're going to plug this point into both equations. Now look, they call this t and s. So I'm just going to assume since t is first and s is second that this is t and this is s. So for t, I'm going to plug in 3. For s, I'm going to plug in 2. So I'm going to make a function table. Here's my x and my y. 3t minus 2s equals 0. It's not x and y, is it? Silly. It's t and s. What a nerd. So t is 3, s is 2. So 3 times t would be 3 times 3 minus 2 times s, s is 2, equals 0. Bring down your equals 0. 9, 2 times 2, negative 2 times 2 is negative 4. 9 minus 4 is 5 equals 0. Is that true? Heck no, it's false. So I know that this is not a solution of this equation. So I don't even have to plug it into the second one, because if it doesn't satisfy this one, then it doesn't satisfy the entire system. And the question was, is it a solution of the system? Well, it can't be, because it doesn't even satisfy the first equation. And it has to satisfy both. All right? Let's look at number 3. Number 3 says, solve the following systems by graphing. Well, look, this is nice. It's already in slope-intercept form. So I look here, and I know that this is 1x, so I know that my slope is 1, and I'm going to show that as 1 over 1 because I need a rise and a run, and my y-intercept is also 1. So I'm going to begin at 1 on the y-axis, and my movement is going to be up 1 over 1. Up 1 over 1, up 1 over 1. Or I could go down 1 and back 1. Down 1, back 1, down 1, back 1. And I'm going to connect my points, and I have just graphed this equation. Now I'm going to graph this one and hope that I can find a point where they intersect. Because two straight lines are always going to intersect one time and one time only unless they're parallel or the same line. Okay, my y-intercept is -2, so I'm going to begin at -2 on the y-axis. And my movement is -2 over 1. So I'm going to go down 2 to the right 1, down 2 to the right 1, or I'm going to go up 2 and back 1, up 2, back 1, up 2, back 1. And I have myself a nice straight line. I'm going to connect my points. And if I do it really carefully, it appears that these both contain the point -1, 0. Well, I want to be sure that this is truly the point of intersection. So I have to determine if this point is a solution of this equation and this equation. It has to satisfy them both. So I'm going to take the point -1, 0 and plug it into both of my equations in a function table. So x is -1, y is 0, and my first equation is y equals 1x plus 1. I'm going to plug in my x and y values. So y, be careful, y is 0. 1 times x, x is -1, plus 1. 0 equals -1 plus 1. Well, if I have one negative and one positive and I combine them, they're out of here, baby. This is a true statement. So this point satisfies this equation, but it has to satisfy both if it's going to be a solution of the entire system. So we're going to put y equals -2x minus 2. And we're going to plug in the point -1, 0 again, plugging it into our second equation. Y is 0, -2 times x, which is -1, minus 2. Be very careful here. 0 equals a negative times a negative is a positive, and 2 minus 2, if I combine those, they completely cancel out and I get 0. True, true. So the solution to this system is -1, 0, and I know it for sure because I graphed it, I looked at it, and I verified it by plugging it into both equations. That's the end of this video. I'm going to stop this and see if I can post this to YouTube.